Have you ever stopped to think about how we generate all the electricity that powers, well, everything? The answer is hiding in a secret connection between two huge forces of nature, a secret that took some of the smartest people of the 19th century to finally figure out.
You know, for the longest time we saw electricity and magnetism as two totally separate things. But then, one discovery changed everything, and it led to this one huge question. If we know electricity can create a magnetic pole, could it possibly work the other way around? Could a simple magnet actually create electricity?
I mean, think about it. On one side, you've got electricity, that spark from static shock, or the current that flows through a wire. And on the other side, you have magnetism, that invisible force in old lodestones, or the thing that makes a compass point north. They just seem to live in completely different worlds.
But then, in the 1820s, everything changed. Scientists like Ørsted and Ampere found that if you run an electric current through a wire, it can actually make a compass needle move. And that revealed a mind-blowing truth. Moving electricity creates its own magnetic field. Suddenly, these two forces were connected.
And of course, this just flipped the whole question on its head. If an electric current can create a magnetic field, then what about the reverse? Could a magnet, maybe a moving magnet, get electricity to flow? That was the big mystery that everyone was racing to solve.
So, the race was on. This next part of the story is all about that investigation, the really clever, hands-on experiments that finally cracked the code.
And let's meet our main characters here. On the left, we have Michael Faraday, working over in England, and on the right, Joseph Henry, in the United States. Now, they were working completely on their own, an ocean apart, but both of them were running experiments that were about to change the world. Faraday's setup was just beautiful in its simplicity. All he did was take a coil of wire and hook it up to a galvanometer. And you can just think of that as a super sensitive detector that can spot even the tiniest bit of electric current. No batteries, no plugs, just wire and a meter.
So first, Faraday takes a regular bar magnet and pushes it toward the coil, and bam, the needle on the galvanometer jumps. An electric current was created out of nowhere. But then, and this is the key part, when he held the magnet perfectly still inside the coil, the needle dropped right back to zero. The current was gone. Then he pulls the magnet away and the needle jumps again, but this time it jumps in the opposite direction.
The conclusion from this was just massive. It wasn't enough to just have a magnet sitting there. What mattered was the relative motion, the movement of the magnet and the coil in relation to each other. That was the secret sauce to generating electricity.
Okay, so we know what happens, but the next big question is, why? Now we have to go from just seeing it happen to really understanding the deep principle that's making it all work.
To get to the why, we need to introduce a new idea, magnetic flux. Now don't let the technical name scare you. The easiest way to picture it is to imagine all these invisible magnetic field lines flowing out of a magnet. Magnetic flux is really just a way of counting how many of those lines are passing through a specific area, like the opening of that wire coil.
And here was Faraday's big aha moment. He realized it wasn't just motion for motion's sake. When the magnet got closer to the coil, more of those magnetic field lines passed through it. The flux increased. When he pulled it away, fewer lines passed through. The flux decreased. It's the change in magnetic flux that's the real trigger for the current.
This incredible insight got a name: Faraday's law of induction. Now, the official definition sounds a little dense, saying the current is proportional to the rate of change of the magnetic flux. But let's put that in simple terms. The faster you wiggle that magnet, the faster you change the magnetic field inside the coil, and the more electricity you make. It's that simple.
But hold on, there's a really cool twist to this story. It turns out that nature doesn't just create a current, it creates a current with a very particular and kind of stubborn attitude.
This is something we call Lenz's law. And what it says is that the electric current you create will always flow in a direction that generates its own magnetic field to fight back against the change you're trying to make. It's basically a law of opposition.
A really great way to think about this is like electrical inertia. You know how a heavy object resists being pushed? It's the same idea. A magnetic field resists being changed. So when you try to push more magnetic flux into a coil, the current it creates literally pushes back at you.
So why does nature do this? Why does it push back? Well, it all comes down to maybe the most important rule in all of physics. There's no such thing as a free lunch.
Just think, if the current helped you instead of fighting you, you could give a magnet one tiny little nudge and it would just get sucked into the coil, creating more and more energy out of thin air. That would totally break the law of conservation of energy. Lenz's law makes sure that doesn't happen. It means you have to physically work to create that current. And the energy you put in from pushing, that's what gets converted perfectly into electrical energy.
And this discovery, wow, it wasn't just some neat little trick for the lab. Its legacy is, and I am not exaggerating, the foundation of our entire modern world.
There's a famous story that when Faraday was first showing off his discovery, some politician asked him, "This is all very interesting, but what use is it?" And Faraday's reply was legendary. He said, "Sir, what is the use of a newborn baby?" He just knew he was onto something huge.
And boy, was he right. That newborn baby, this principle of electromagnetic induction, grew up. It became the science behind the AC generator, the incredible machine that powers almost our entire civilization.
So how does a generator work? It's literally just Faraday's experiment, but on a massive industrial scale. Instead of pushing a magnet back and forth, you use some other force, like water falling through a dam or super hot steam, to spin a giant coil of wire inside a powerful magnetic field. That constant spinning means the magnetic flux is constantly changing, and thanks to Faraday's law, that induces a steady, continuous flow of electricity.
And this is the beating heart of pretty much every power plant on the planet. It really doesn't matter how they do it. A hydroelectric plant uses falling water. A thermal plant burns coal to make steam. A nuclear plant uses fission to make steam. They're all just different ways to do the exact same thing. Spin that coil inside a magnet.
And the scale of this is just, it's hard to even wrap your head around. A single big modern generator can pump out 500 megawatts of power. That is enough electricity to turn on 5 million 100-watt light bulbs, all at the same time. All of it coming from that simple, elegant idea of changing a magnetic field in a coil of wire.
So from a simple question about two forces, to a little tabletop experiment, to a principle that literally lights up our entire planet, Faraday's newborn baby really did grow up. And it kind of makes you wonder, right? What seemingly small scientific discovery happening today is the newborn that's going to power the world tomorrow?